Hey guys, let's talk about let's jump into our second video for environmental science for this year. We're going to pick up on some of the themes of the first video with sustainability, and then we're going to jump a little bit into science and the process of science and some of those things that we talked about in class already in the past week or so. So to pick up on the theme from the last video, we ended talking about the idea that our main topic is sustainability. And so we're going to jump right in here with the idea of sustainable development. We know that, especially in our society, that economic growth is pretty important. That society as a whole isn't going to just, sort of fold up and say, no, that's okay if the economy shrinks. We'll be okay with that. That just isn't the way that modern society is set up. We require pretty much economic growth, and we get very worried and upset if there's not economic growth. There's not enough jobs for everybody. That's obviously a pretty big problem. So sustainable development means that we're going to balance that desire for economic growth along with the idea of balancing things so that future generations can also grow economically and have a certain amount of human well-being. So to do that, we need to have some conversations about what human needs are. So let's talk real briefly about what a couple of those basic human needs are. And some of them are pretty obvious. I mean, I think food and water are probably the two biggest ones. We're going to talk a lot about food and water this year, environmentally, and pollution and growing things and the green revolution and all those sorts of things. So very environmental topics there. I think shelter obviously is another basic human need. We're not going to talk quite as much about that, but I think there are certainly some sustainable options there that we will discuss. And then there's also some other, more complicated needs than that. Your book points out this idea of biophilia, and I spelled that terribly wrong. Biophilia. I didn't actually spell it wrong. I just wrote it badly. But what biophilia means is that the idea that we love life. We want to be around things that are living. This is why even in a place like New York City, where you have this giant, sort of almost concrete jungle, type structure, that you have a big area in the middle, Central Park, so that people can get out and enjoy other living things. And so that's one of those complex needs. And of course, we could have other things like love or emotions or any of that stuff. Now, whether or not that's a true need, I think psychologists would say that yes, it is. And we could debate those things. We're obviously not going to talk a lot about those things in an environmental context. But those complex needs, those human needs, all sort of tie together. And those are things we need to consider when we talk about sustainability. One of the things that we're going to talk about just over and over and over again this year is the idea of an ecological footprint. Okay? And you've probably heard that term used before. If you listen to NPR or read any articles about environmental issues in general, they're going to talk a lot about the ecological footprint. And basically what it is we're going to take all of everything that a person consumes and sort of crunch it down and give it a number that's expressed in an area of land. And we're going to talk more about this a lot later in the year. But basically it says take all of the foodstuffs that we use and all the property that we have and all the energy, all the things that are consumed to produce our energy, all the things that are consumed to build your car and your house and your iPod and your iPad and all of those types of things. All of those things leave behind an ecological footprint. And one of the things that we'll see as we go throughout the year is that we're getting to the point in the world where other societies want to have the same sort of lifestyle that the United States has. And the fact of the matter is the carrying capacity of the Earth to sustain that just isn't possible. It would take about 5 Earths for everybody that's currently on the Earth to be able to have the same type of lifestyle that we have in the United States today. And so that's something to sort of think about when we consider these issues. And again, we've talked in class about how we're pretty blessed and privileged in the United States. And so that means that, if everybody wants to emulate that lifestyle, that maybe something about our lifestyle needs to change as well. So just keep in your mind that the idea that the footprint that we talk about a lot, the ecological footprint, has to do with consumption and how much land and how much of the environment, how many environmental resources it takes to have that level of consumption. So here's one of the things that I want you to think about. Okay, we're going to talk about this in class and do some activities with this. Basically, what makes up an ecological footprint? Okay, and like if you were talking about your own personal ecological footprint, what sorts of things make that up? You know, what all pours into that? What sorts of things do we consume? And so when you're jotting down your notes here and you're going to come back to class, hit pause here for a second and jot down a few ideas so that when you come to class, we'll have a few things to talk about in terms of what would make that up for us. So we're going to sort of segue into our next area here. We're going to talk a little bit about science as a process. Now, we've talked about some of this in class already. We talked about some myths of science, and one of the myths of science, if you remember, is that science always occurs by the scientific method. So we're going to run through real quick sort of the traditional scientific method, and we're going to talk about ways that it is true and then some other attributes of it, and sort of take it further maybe and get some more definitions than what we've had before. So essential scientific method, we're going to observe and question. Okay, we're going to come up with some sort of question. We're going to form a hypothesis about that question. So like, why does this particular thing happen? I believe that this thing happens because of this. Okay. And then we're going to collect data on it or experiment. Now, typically in the normal scientific method that you learn, it's pretty much all just says experiment. But really what we're going to see, especially in a lot of the cases that we're going to talk about environmental things, is sometimes we're not necessarily doing experiments so much as we are collecting data, perhaps to prove or disprove a hypothesis. And then this would be the sort of normal draw conclusion state and interpret results. And then to disseminate findings. That sounds like it's a pretty verbose sort of thing, but that basically means to, whatever your results are, to get them out there so that other people can look at those results and see whether or not they believe that those things are true. Now, of course, this is in some ways a circular process because we take that interpret results, and if our hypothesis was false, we will very often go back and form a new hypothesis and then work from there. Another thing that you may not have heard this term before, but the term null hypothesis is pretty important because basically a null hypothesis is something that you can prove wrong. And a lot of times in science it's very easy, or it's easier, I guess, to prove that something is incorrect than to prove that something is correct. Remember when we talked about science that we said that we can gather a lot of evidence to show that something should be true, but we can never really absolutely prove in the positive sense that something is true. On the other hand, we can prove very often that things are wrong. Okay, so a null hypothesis leads into that idea. Null meaning sort of empty. Just the idea that we're going to try to prove that something doesn't work in a certain fashion. And that's a very valuable way to go about some of this research. So we're going to talk a little bit about collecting data. That's the second point here. Okay, so observe and question, form hypothesis. We talked a little bit about the null hypothesis. Now, about data, there's a few things that we want to get straight here. A couple of definitions. First off, very important science to have replication. Okay, usually you've heard this term of things being repeatable. Okay, and so that's what replication means, is that you have several sets of data that you've done a lot of trials. You've probably done the same experiment multiple times, maybe multiple trials within each experiment. A lot of times if we're collecting data on a certain area or a certain number of species or something like that, we're concerned with a sample size. And that's basically how many times that measurement does get repeated or does get replicated. Really important, if I said that, if I took a sample size of 2 students and said every student in the class has an average of, a 95 because I only looked at 2 students' grades, that's different than if we looked at 100 students' grades and saw what all of their grades were together. So in general, the bigger the sample size, it sort of helps lend some credence, lend some reliability to the data, just like replication and having more and more of that data does. A few terms just that I pulled out of your book here as I was setting up for this. Accuracy, precision, uncertainty. You probably know what these terms mean from other science classes, but real briefly, remember accuracy is being close to what the real measurement is. Okay. Precision is being your measurements being really close to each other. So in terms of like the bullseye, accuracy would be that I threw 3 darts and they all hit right in the bullseye. That's accurate. If I threw 3 darts and they all hit like in the 20, then I wasn't very accurate, but I was very precise if they're all grouped up together. And then if they're all over the place, it's neither accurate nor precise. Uncertainty is how far away you are from being accurate. So how far away you are from the actual measure. And you can look those terms up, but I mean, I think those are pretty common. We've certainly used those before in lots of other science classes. So I don't really think that those are anything particularly new. Um, some other important things with collecting data, and you're going to hear a ton about this year, and really in any good science class, you have to have a control, okay, most of the time. Not all the time. We're going to talk about some of those situations. But in general, you want to have a control. And what a control is that's the group that experiences all of the same conditions as what you're running the experiment on. So in a typical experiment, you have a control, and then you have an experimental group. And they all undergo exactly the same thing. So like if we were trying to grow something, okay, and we had two containers, and one is the control and one is the experiment, okay, everything happens then the same. I add in the same amount of water in both of them. I give both of them the same amount of sunlight. And let's say that my experimental factor, my variable that I was trying to test, is whether or not a pesticide hurts it. So the control gets everything that the experimental group gets except for that pesticide. Okay, same nutrients, same water, same amount of sunlight, everything is the same. You want to test one variable, and that's the real important part here, single variable. If you can, that's the ideal, is that we would ideally prefer to test a single variable. Now, that is not always the case, okay? It's not always possible. We're going to talk about that, but that is what we're shooting for most of the time. When you get to interpreting the results, I just want to sort of pull two things in, and hopefully you probably know these from your English classes and your history classes, but just real briefly, there are two sort of main divisions in reasoning, and really we use both of these on a regular basis, but they're inductive and deductive reasoning. And the reason I have these triangles here is that's sort of the general representative rule of what these two things mean. Inductive reasoning means that I'm taking specific facts and I'm applying them to make a broad generalized rule, okay? So like I say something like, hey, every dog that I've ever seen is brown, and so therefore all dogs must be brown. I take the specific facts of the dogs in the sample set that I've seen are all brown, and I apply it and make a general rule from it, okay? You probably already see some flaws in that, okay? And there's flaws in both of these. Deductive reasoning would say that I take a general rule or principle and then I make a specific fact from it. So I've got a broad rule and then I narrow it down. Okay, so inductive goes from narrow to broad and deductive goes from broad down to narrow. Okay, so an example of deductive reasoning, if I said, okay, a lot of times it's a statement of some primary facts, and so all dogs are mammals. All mammals have hearts, and therefore all dogs must have hearts, okay? So the general rule being that all dogs are mammals can lead down to a more specific fact that all dogs have hearts, okay? Inductive, deductive reasoning, okay? And again, I'm sure you guys have talked about that in other classes, but just wanted to put that out there that you need to sort of keep that in your head, that we can induce facts and we can deduce facts. When we disseminate results, that's, the publishing of results, putting them out there, getting someone else to peer evaluate them or something like that. That leads us into two categories. And I put up theory and law, and the only real reason I put these here is because I want to make real clear to you guys that theory in the scientific sense doesn't just mean like an idea that someone came up with, okay? And the example I always like to use is, one of the biggest theories that we talk about all the time is atomic theory. Atomic theory, pretty well settled. I mean, we're pretty sure that's the way that it works. It has been tested hundreds upon thousands of times, and the evidence is borne out that that's the way it works. Okay, so a theory isn't like, hey, come up with this theory. That's sort of the normal parlance. That's not how we use the word theory in science. Theory is something that's pretty well established. Now, something that is more well established, and what I mean by more well established is there has never been an instance in which that has not occurred in that way. That is a scientific law, okay? Theory, law, almost the same thing in most cases of what we're talking about in science. When we talk about atomic theory, we pretty much accept that as a scientific law, even though it probably technically, since it's only been 100 years or so since it's been around, could go into it a little bit further. So real briefly, let me wrap up by talking about a few challenges that we have in environmental science, okay? So I got 3 of them listed here, okay? First thing is that things are really complex, okay? We're talking about nature. We have thousands upon thousands of variables, and it's really hard for us to isolate and get that ideal that we like in science of just having one single variable. It doesn't happen very often. A lot of times what we'll have is we'll have natural experiments, so that like something will happen naturally and we go in and investigate it, and something that we probably wouldn't ever do. So like damage from an oil spill in a coral reef. We wouldn't purposely damage a coral reef just to test it, but if an oil spill happened, we would then go in and gather data from that. Okay, that's a natural experiment. The reason that we wouldn't do a lot of those things is that there's a lot of complexity. You can't really simulate a coral reef as a whole in a small laboratory situation where you can control all the variables. So there's a lot of complexity. A lot of times there's a lack of baseline data or data. What baseline means is this is the initial conditions, okay? And so we know what this would be before that happened, okay? I think climate change is a good example of this. We have some data about what climate was hundreds and thousands of years ago, but we don't have the kind of data that we have today. We don't know all of the factors that we've known for, like, say, the past 100 years that we've really been collecting that data. And so sometimes it's hard for us to make real good judgments about this has changed by this much because we don't really know always what the initial conditions were. And then, of course, this goes back to stuff that we talked about in class. There's subjectivity. There's bias sometimes in it, okay? Some things are subjective depending on our cultural interpretations, our political interpretations, all of those things. And those things are always going to bear a big burden for us in environmental science because it's really hard to separate out these issues. People get really passionate about a lot of these things. In chemistry, things are pretty straightforward. There are numbers involved, and so the passion, for arguing one side or the other. No, I mean, reactions balance, and stoichiometry is what it is. And, in physics, the, laws of momentum and stuff like that, they're pretty well established. So there's no bias there. But environmental science, there's a lot of interpretation going on, and therefore there's a lot of bias. Okay? I hope all of that helps you guys out a little bit. That's pretty much most of Chapter 1 for us. Sort of a baseline of what we're going to do for the year, and then we're going to dive into some more specific issues as we go on. Thanks a lot, guys.